Good afternoon, everyone. My name is Zach Carrico, and today I'm going to be talking about an array-based machine learning platform for early cancer detection. So although I'm presenting this, many people at Freenome contributed to this work, and I would like to thank all of them. We have a fantastic group of engineering, scientists, different types of product management, business, and all different types of media-related functionality that have been very helpful in putting these slides together. So I'm going to be breaking this talk down into 4 segments. So the first one is going to be talking about Freenome and early cancer detection. That's really the mission of Freenome. The second one is machine learning applications. And so that's going to be, the two I'm going to be focusing on are cancer risk prediction, as well as cancer detection from blood samples. And in the third part of the talk, I'll be talking about why we decided to use Ray. And finally, I'll be describing how we're using Ray and Freenome's machine learning platform. So at Freenome, we are 100% focused on early cancer detection. So cancer is the #2 cause of death in the US and globally. But early cancer detection can have a very big impact on survival rates. And so what you're seeing here on the right side is a plot of survival over 5 years, and then the x-axis is the different types of cancers. And then the lime green bars are this localized cancers, meaning like it's an early stage, and then the purple is metastatic, so it's like a late stage. And so if you can detect cancer early, you really can greatly improve the survival outcome for people. Freenome is a company which was founded in 2014. We have received over $1 billion in financing since then. We have over 50 biopharma and academic partners and over 450 employees. The first product we're working on is for colorectal cancer detection, and as well as advanced adenomas. So colorectal cancer is the second deadliest cancer in the United States. But when caught early, it is highly treatable. You can get about a 6x improvement in the survival rate over 5 years if you can catch colorectal cancer early enough to treat it. So our objective at Freenome is to make colorectal cancer screening easier, and we want to do that by providing an accurate and accessible blood test. This can increase colorectal cancer screening adherence because it's just simply easier to do it than a colonoscopy. This can lead to an improvement in survival rates because we're able to catch cancer earlier. Colorectal cancer is just the first cancer of many that we plan to target. And so we've been working on other cancers as well, and all of this relies on the same platform. So we have a multiomics platform, and I'm going to be describing that later. The machine learning applications that I'll be describing in this talk are 2 of them, and one is cancer risk prediction, and this is using real-world data. So in this case, this is data that is related to patients' healthcare. And the quote related to this is that our goal is to identify the right patient for the right screening tests at the right time with clear next steps. That is the goal of cancer risk prediction at Freenome. And so what you start with here is you start with real-world data, and you do feature extraction on it. And you train a machine learning model on that, and from that you can predict whether or not a patient is likely to be at high risk or low risk for a certain type of cancer. The second machine learning application that I'll be describing in this talk is cancer detection using multiomic data from blood. So multiomic data is data that comes from different omics technologies, and there's many different omics technologies out there. You have genomics, transcriptomics, proteomics, epigenomics. We use many different types of omic technologies to analyze blood at Freenome to provide us with a signal that we can use to classify models that can be used for cancer signal detection, or in the good case, no cancer signal is detected in the blood. So those are the 2 machine learning applications that I'll be describing. And I also want to talk about why we decided to use Ray for these machine learning applications. So we chose to use Ray because it really enables fast model training with large volumes of data. So Freenome's data is already very large. Multiomics data can generate enormous amounts of data because of just the number of different biomarkers you can measure and the number of modifications to those biomarkers. Ray supports distributed data parallel model training, and it supports specifically 4 libraries that we care to use. Those libraries are XGBoost. We want to use that for the risk prediction training. We want to use real-world data with XGBoost, and we have large amounts of it. And then for the omics-related training, for when we're trying to detect cancer, we want to use PyTorch for that. And Ray also supports distributed data parallel model training with PyTorch. It also supports different types of HPO using RayTune, and it has integrations for the different types of monitoring tools that we use, including MLflow, TensorBoard, Prometheus, and Grafana. And it does this in a very simple and elegant way. You can use callbacks for MLflow and TensorBoard. Out of the box, it immediately logs things such that you can access them and use them in Prometheus and Grafana. And so it creates, basically, it has pre-built dashboards that you can use out of the box, which is very convenient. I wanted to talk about distributed data parallel model training for a moment, because this is really one of the goals of ours when it comes to using Ray. So in this case, what we're doing is we have large amounts of data, and if we're going to try and train all of that data in one machine, it would take too long because we have to do many, many iterative batches. What we can do instead is you can split up that data into separate processes, and then on each process, in each separate process, you're going to create a copy of the model you're going to be using. And so within each one of these processes, you're going to train the model on a unique piece of that data. And then after a certain number of iterations of training, you're going to synchronize the models, such that they all have been summed up, the usually gradients in this case. And this allows you to synchronize the models, and at the end, you're going to have the same model, which you can return and save. There's different types of modeling updating strategies, such as allReduce and ParamServer. The libraries that I'm going to be discussing today are PyTorch and XGBoost. Both of those use allReduce, so that's what will be referred to in this talk. So the first machine learning application that I want to describe is cancer risk prediction model training. The objective of this is that we want to be able to predict if a person will be diagnosed with colorectal cancer within a certain time frame. The data that's being used for this is electronic health records and medical claims data. The data sets are tabular in nature, and we have many millions of patient observations. Each row represents a summary of a patient's clinical history through a given date. And this includes over 1,000 features such as age, sex, years since the first and last diagnosis of different types. And so we have large amounts of features, large amounts of data for this. And because of the tabular nature, we wanted to use XGBoost for this. There are many other reasons that XGBoost is appropriate for this and what we wanted to use. So XGBoost is a gradient-boosted decision tree library. It's commonly used, and it's open source. It provides generally very good performance on tabular data. It'll natively handle missing data. It's interpretable in terms of it'll provide the feature importance measurements when we need to interpret the results. It'll also capture nonlinear relationships and interactions. It's relatively fast. It's parallelizable and can be sped up with GPUs. It also prune trees backwards from the maximum depth to optimize loss. I really like this illustration of XGBoost from this great blog post, which really goes into the math and explains things clearly about XGBoost. It's called explain.ai gradient boosting. So what gradient boosting is, it's training models in a sequential fashion. And so the example here is that we have a golfer aiming for a target value. That's the Y over here. And the golfer takes a shot. It's short. And the value prediction is this F0 value. And so what you can do with this is that we know our true value, because it's supervised learning. And so we'll take the mean squared error of this. And then you can train the next model, another weak learner, on the negative gradient of the loss function of that mean squared error. And this will allow you to make a second prediction. And the second prediction will get you closer to the target value. And so you keep doing this, this gradient boosting, this sort of sequential training of various weak models. And at the end of this, you can sum up all of the models to produce a stronger composite model. So XGBoost Ray makes distributed data parallelism very easy. So what I'm showing here is a simplified version of the code. I'm leaving out some things, but really it is this simple. We have the XGBoost Ray.train call, and what we're passing to that is a RayD matrix. So XGBoost has these particular types of matrix objects that it needs. And what we're passing in this case is we're passing, you can pass Parquet file paths. Our data has been already sharded into Parquet files of the appropriate size. And so in this case, the example is we have a train1.parquet file and a train2.parquet file. And then the other thing I'm highlighting here is we're specifying that there's two actors being used for the distributed data parallel model training. And so in this case, the Ray driver will create these two workers. It will assign each a unique rank. And then in the next step, the workers will load the data. And so you have some sort of source of your data. It'll load one. They'll have different pieces of data in each worker. And then you're going to start the model training. And you can go either for one iteration or multiple iterations. And then after you've trained the model on that unique piece of data in each worker, you're going to use rabbit all-reduce. That's what XGBoost uses by default for the synchronization of the models across the workers. And then you can keep repeating this process of loading more pieces of data and more training. And you'll continue that until either things plateau or the max number of boosts is reached. And at the end of this, once you've used all your data and you've trained the model, you can return the model from one of the workers to your head node, and then it'll be checkpointed. So I'm going to describe some of the actor failure recovery options that come out of the box with XGBoost Ray. This has already been described in good detail by Kai Frick and Michael Muley in a previous Ray Summit in 2021. And there's also some great Uber blog posts about this, and that's where this figure is taken from. I wanted to highlight it here just because I think it's great functionality and it's worth knowing about if you're going to use XGBoost Ray. So there are really two fault tolerance options. The first sort of row up here is showing without fault tolerance what will happen. And so in the very first column, we're seeing all the workers loading data. That's the ones in yellow. And then in green, the second column, we're showing them training. And then in the third column, worker 3 fails. And so without fault tolerance, what will happen here is that all the other workers will stop, and then everything has to restart, and then you can restart the experiment. So that's without any type of fault tolerance. XGBoost Ray provides two types of fault tolerance. You have non-elastic training and elastic training. And so what's happening in non-elastic training is that you have the same loading and then training, and then when one of the workers fails, if one of the workers fails, what will happen is that the other workers will be paused at that point until that worker 3 can restart, reload the data, and sync back up with the other workers, and then training will resume. The second type of fault tolerance is elastic training. And so again, you have loading data, training, worker 3 failed, and in this case, all the other workers just keep going in terms of training. And they leave worker 3 behind. It will restart, and it'll start training again. You end up actually training a little bit less than you would, and it'll finish early. There's a marginal impact empirically on the performance of the model. And so this is the second basically failure recovery option that you can use out of the box using XGBoost Ray just by specifying it as one of the parameters. I encourage you to look at the blog posts in the Ray Summit 2021 videos for more details on that. So Ray provides two options for using XGBoost. One of these is the XGBoost Ray library, which I've been describing. The other one is the XGBoost trainer. And that is a trainer subclass of Ray, and that wraps XGBoost Ray. So a comparison of these two, we did a simple comparison. There's a couple things that we want to be able to do. One of those is to load Parquet file paths directly. The other one is to be able to use fault tolerance options, like I described. And then the third is we just want it to be as fast as possible. So for XGBoost Ray, the library itself will allow you to pass Parquet file paths. It has fault tolerance parameters built into it, and it trains pretty fast. But XGBoost Trainer, it doesn't allow you to pass Parquet file paths directly. You would have to put them into a Ray matrix, a Ray dataset object, and then you can pass the Parquet file paths. And then for the fault tolerance options, these can be accessed, but you sort of have to sneak in there and access them via private attributes to be able to use the XGBoost Trainer. And empirically, it's just slower than using the XGBoost Ray library directly, which makes sense to a certain extent because it's wrapping the XGBoost Ray library. So there's going to be a certain amount of overhead. We just decided to go ahead with XGBoost Ray. One of the things we want to be able to do with it is we want to be able to do cross-validation. Cross-validation is a really common technique in scientific circles for improving the measurement of the performance of models. And so what's happening here for cross-validation is that you're going to take all of your data, and then you're going to split it into k-folds. And so in this case, you can split it into 4 folds, or the example is for 4 folds. And in each split, one of these folds is going to be the test, and the rest are going to be the train. So in this case, we have the first fold being the test, and the rest are train. And the next split, the second fold is the test, and the others are the train. Each one of these splits, we're going to measure the performance of the model. And then at the end of measuring the performance of the model on each one of the splits, we're going to average the metrics for all of them. You end up getting a better performance metric measurement overall. The accuracy of the performance measurement is superior using cross-validation. So Ray doesn't provide this option out of the box for cross-validation. And so knowing a little bit about how to manually distribute things using Ray, you can use the ray.remote. You could create a function called cross-val, and then you could pass in the XGBoost ray.train within that function, and just pass the split data to the XGBoost ray.train call. And in this case, the next call will be to running ray.remote across this function, and you can do this in a list comprehension, and that'll give you the futures. And then when you do the actual ray.get, you'll do a blocking step until you get the results from all of these calls to the cross-val function. So that was our original implementation of this. This results in an error. So I put this error into a GitHub issue. It may be that this type of strategy for doing cross-validation with XGBoost Ray is just not possible. Maybe there is a way to do it, and at some point maybe we'll find a solution to that. But if anybody has any ideas, I'm more than happy to hear it. We're trying other types of cross-validation as well, such as nested cross-validation for hyperparameter optimization. Our solution currently is to serialize cross-validation. So rather than parallelizing it to make it as fast as possible, you can serialize the training of the XGBoost model on splits of data. And so in this case, all you do is you take off the @ray.remote decorator, and then you can call the list comprehension on here. In this case, it'll run it sequentially, so it's going to be k times slower, where k is the number of folds used for the cross-validation. It'll work, it's slower, depends on your application if you want to go this route. We also wanted to evaluate what it's like, basically how much of an improvement can we get when we start to parallelize training using XGBoost ray.train. This is unrelated to cross-validation. This is just splitting, again, the data into shards of data, putting those in different processes, and then training the model on each one of those processes. And so what we're showing here on the y-axis is the time it takes to train, and then on the x-axis is the number of workers. And so this first data point here is for 1 worker, then we increase to 2 workers, 4 workers, and 8 workers. And what you see is you see a dramatic reduction in the amount of time it takes to train. That's exactly what you want to see. This is what's giving us our speed improvement when we start to use distributed data parallel model training. On the right is just a log-based 2 version of the exact same data, trying to give you a little more sense of the linearity you might be able to see with this. So we're really happy about this. This is really good performance. It allows us to use increasing amounts of data without taking increasing amounts of time necessarily. The other thing is that XGBoost Ray does a great job uniformly loading this data and handling all these different workers. So we have over 67 million observations and over 1,000 features that we're working with for the risk prediction. And the data is partitioned to evenly sized Parquet file paths. And Ray is able to uniformly load this data across all these different workers. So we've got 30 64 gigabyte workers. And you can't see these numbers on the right here, but this is a plot of, on the y-axis, the node memory, which is a combination of the heap and the object store, and on the x-axis, the time. This is taken straight from the default dashboard that's created for Grafana for you by Ray. And what you can see from these numbers, if you could see them, is that the range of memory used by each one is between 31 and 36 gigabytes. And so there's a pretty narrow range in terms of the memory used, and it's pretty uniform. So that's great. There's no bottlenecks. You're not seeing certain nodes using up a ton more data than other ones, which would become problematic. That's the end of the part on cancer risk prediction. Cancer risk prediction. And so now I'm going to talk about cancer detection model training. So the objective of this is that we want to be able to predict the type of cancer and the cancer stage from blood samples. So here we're working with multiomic data that's collected from blood samples. So we collect blood from patients with and without cancer in this retrospective study so we can build these machine learning models. We have a prospective study where we take these trained models and we have the largest colorectal cancer cohort for screening and for blood-based cancer ever. So we have about 35,000 patients already enrolled in this clinical trial. But this is the actual training stage where we're doing things retrospectively. And so we have labeled blood as coming from a cancer or non-cancer patient. And what we can do here is we can, from that blood, do various types of multiomics analyses. Again, these are things like looking at the proteomics, the genomics, the transcriptomics, the epigenomics. This produces a vast amount of data. And for this data, we want to use PyTorch. So for this, one of the reasons we want to use PyTorch is that it's open source. Just like Ray, it's wonderful when it's open source. You can see everything, and it's more heavily tested. It's relatively fast because you can parallelize it. It has first-class support for deep learning. It's flexible enough to be used for non-deep learning model development. And it natively handles multidimensional arrays. In addition, it has extensive GPU support. Ray provides a torch trainer, which is a subclass of the trainer class. And this allows you more flexibility than the XGBoost library. Because what you can do here is you can pass in a function to the torch trainer, and you can customize that function as much as you want to. The XGBoost Ray.train, that's more of a closed system. You're not passing in a function to it. So in this case, we can define our training loop that we want to pass to the torch trainer. And within that, the typical things that will happen are that you're going to be loading the data, training the model, evaluating the model, and checkpointing the model. So here is just a little diagram of you have one torch trainer. If we're using distributed data parallel model training, the data will be loaded onto each one of these workers, unique shards of data. And it'll be trained, and then you can use functionality that is really greatly enabled by Ray for distributed data parallelism when you're doing model training. So like I was saying, Ray simplifies this process. So if you're not using Ray for this, what you would have to do is you would have to manually go in and provide information to the distributed data parallel class for PyTorch to be able to do this type of thing. Ray provides some basically helper functions to make this really easy to do. You have this prepare model helper function. And so what this will do is it'll move the model to the device. It can be a CPU or a GPU. And then it'll also prepare the PyTorch model with the distributed data parallel class, which allows you to use distributed data parallel model training. You can also specify to use the fully sharded data parallel class with your PyTorch trainer. In addition, it also provides another function for preparing the data loader, conveniently named prepare data loader. And so what you can do here is it'll move the data to the CPU or GPU. It'll also apply distributed sampler to that data loader. So what this means is that your your data loader will be sampling unique pieces of data from the entire data set, which is important because you don't want to be resampling the same data across every worker. What this would look like in practice is if you were going to write this train loop per worker, you can pass in your data loaders, your train data loader, your evaluation data loader, your model, and the number of epochs you want to run for. And you would apply the prepare model, you would apply the prepare data loader, and then you do your epoch training. So you'd go your fit, you do your evaluation calculations, and then you'd be reporting those metrics. And at the end, you would be checkpointing your best model. And so when you use Torch Trainer to do this, each one of these workers is going to be running the same training loop. And because of this prepare model and prepare data loader, although they're running the same training loop, they're actually accessing different data and they're training different models. And after a certain number of iterations of training, you're going to do an all-reduce synchronization, and that'll synchronize the models across all of the workers. We also wanted to evaluate the basically improvement that we can get from using this distributed data parallel plus distributed sampler option that's really conveniently built into PyTorch, and you can access using Ray very easily. So again, we're showing the time to train on the y-axis and the number of workers on the x-axis. And so here we see that with one worker, if we double the number of workers, We get nearly a halving in the amount of training time it takes. And we keep seeing that as we increase the number of workers, we decrease the amount of time it takes to train. Very similar to XGBoost Ray. And this is just, again, using log base 2, so you can see a little bit more of the linearity of the plot. So the thing that's very important for us, we are creating a product which is going to be approved, we're working towards approval by the FDA. Everything has to be completely reproducible. And so we are making use of things like the MLflow logger callback to be able to log everything to MLflow such that it'll persist indefinitely. One of the things we also want to do is we want to make sure we're recording all of the data and information we need to make each experiment reproducible. So in this case, what we're showing is just, this is a screen capture from MLflow, and we can see the entry point is ray-torch.py. And then what we're recording is other information necessary for reproducibility. These include the git hash, and in addition to the git hash, we want to know whether or not someone forgot to commit something. This will happen in the case where someone's just tweaking little things and they're not committing every little thing. If, in most cases, when you're running a large experiment, everything should be committed before you start it. If someone forgets, we'll have a flag which says, hey, there was something that wasn't committed. In that case, we also have a tarball of all the code that was used to run the experiment. So we're storing that as an artifact using MLflow. That allows you to recover the experiment even if you didn't commit everything. In addition, we're saving the experiment configuration as a config.yaml file. And we also save all the CLI overrides. So our MLflow, our ML platform has the ability to be executed using the CLI, and people can override certain parameters over the CLI. And so we're recording those. And in addition, we're using array cluster YAML. So that's specifying everything about the array cluster, including the Docker image, which is very important for reproducibility. And so we're also saving an artifact of the array cluster definition. In summary, so Freenome uses machine learning to predict cancer risk and detect cancer. And so it's going from real-world data to feature extraction to trained models to being able to predict whether or not someone is at high risk or low risk of cancer. In addition, we take blood, we can do multiomics analysis on that blood, we can train machine learning models on that, and that'll allow us to detect whether or not someone has cancer or does not have cancer. Ray simplifies distributed data parallel model training a whole lot, and we're very grateful for that. Cross-validation is something which Ray does not provide, and so we've been working through different iterations of this. I've not presenting on the nested cross-validation work we've done, but I've also have some implementation design ideas which I would love to run by some people in terms of like if this is the most efficient way to be doing it with Ray. So if there's any experts out there on Ray, I would love to talk with you afterwards. And I want to acknowledge all the fantastic work of everybody who contributed to this presentation. So I'm within the research platform team, and then the scientists are within the risk prediction team and the multiomics team. And this is the team which is doing cancer detection using multiomics data. And I really want to thank Ray and Anyscale for providing a really great product and making it easy and accessible for everyone. And I also want to thank the Ray conference organizers and everyone who's doing AV work out there for making this a very great conference to attend. And thank you, and I'll answer any questions now. Yeah, we're not at liberty to disclose where all the real world data comes from. So we have partnerships with different companies. Yeah. How much data do you need to train a meaningful model? So the first question, yeah, it's a good question. So it's like, how much do we need? I don't know the direct answer to that. So basically, you can do estimates of how much of an improvement you get as you increase the amount of data we're using. But I haven't seen that type of plot from the risk prediction team. Yeah. Yeah. Sorry, can you say it a little louder?
So for this project,
Uh-huh.
how much do you
Oh yeah, so for this project, for the results I was presenting, it was over 67 million observations of patient data and about 1,000 features extracted from that. Yeah. Yeah, please.
First one follow-up question. How much data did you have, like how many cells did you have for multiomics data? And what models on multiomics data have you found most useful and had some pre-training with beneficial?
So the cells part, when you say cells, what?
How many multiomics? I'm assuming it's like single cell.
Oh, no, it's not single cell. Yeah, so we're primarily, so this is a scientific question. I always appreciate these. So we're using whatever we can get from the blood, from the plasma. This is cell-free DNA. And that's one of the things we're using. Cell-free DNA is one of the primary things. You can measure both, obviously sequence that, as well as look for any type of epigenetic modifications to that. You can also look at the expression level of different proteins in the blood. But it's not single cell sequencing like that. Yeah. I don't know if I answered your second question, but let me actually, because I've got, oh, I think I'm over time? I can't tell. But let me, couple more. You had a question?
I was wondering about the, can you say the ratio of, concerning the cancer detection,
Uh-huh.
the ratio in the data of actual, of cancer to non-cancer
Yes.
patients?
Yeah, so we create a pretty balanced data set. I don't know the exact numbers off the top of my head, but for the retrospective training, we deliberately have like a large number of cancer samples as opposed to just sampling like the real world population relative frequencies. Yeah.
For the reproducibility
Uh-huh.
department, how do you deal with fault tolerance issue? Like if you have something that comes up where something has to restart, or you're using one of the strategies where it doesn't lead to a different result in the end. I think you mentioned there was one where one of the workers fail after reload
Yeah.
data, but you would keep training the other ones and it could lead to a different result.
Yeah, very good question. So that we don't use the elastic training. We use the non-elastic training for that reason. Good question.
So does the FDA mandate that you have to do that approach, the one that doesn't lead to variable behavior, or is that a self-selected choice?
Pretty much everything is, with the FDA, is we try to do our absolute best to make things as robust as possible. And then we have conversations with them about what we're doing, and then they give us feedback on that. And so really it's mostly self-driven in all of this to just make the best, most solid product possible. And then they can give us feedback if we can do anything better.
Last question.
Okay. I think you maybe had your question, your hand. Yeah.
Yeah, I'm curious if you experimented with vertical scaling, because I know you did horizontal scaling with like longitude for the 8 nodes. But what about, I think your machines for 164 are by size, right? What about vertically scaling that to the largest possible instance?
Yeah, that's a good question too. So, so the question is like vertical versus horizontal scaling. I apologize, I didn't repeat all of everyone's questions. So it's for us, we're really aiming for being able to use the smallest, most horizontal strategy. So smallest compute size, most horizontal strategy, because that is the most scalable long term. And so you could increase the vertical one. We didn't test that. We have originally when people started, before we had the option using Ray to use this, people could use the vertical solution for it. But when there was out-of-memory issues, there was no place to go. You couldn't, there wasn't any sharding solution in place. And now I know there were some other questions. I really appreciate all the questions. I'd love to answer them afterwards.